Well, this fourth podcast in the hypoxia series is a little more difficult, but let's give it a shot and see what happens. What I want to do is look at the way the body detects hypoxia, look at how the body responds, and we want to learn that the way the body responds is an attempted compensation. It's very clever. When the body realizes there's hypoxia, there's physiological things it can do to try and compensate for that hypoxia, to try and maintain the oxygenation of the cells. Now, if you've got the black pathophysiology book, open it to the hypoxia chapter and look at the oxygen flux. Look at the oxygen flux equation. But if not, I think you're going to have to write this down because it's a bit hard to hold in your head. The oxygen flux equation. Now, oxygen flux is the way that oxygen travels from the lungs to the tissues of the body. The movement of oxygen from the lungs to the tissues of the body is described as oxygen flux. And it's defined in this way. Oxygen flux equals cardiac output times arterial oxygen saturations times hemoglobin concentrations. So write that down. Oxygen flux equals cardiac output multiplied by arterial oxygen saturations multiplied by hemoglobin concentrations. So the oxygen flux, that is the movement of the oxygen from the lungs to the tissues, is determined by these three factors. Firstly, the cardiac output. And the cardiac output is the volume of blood pumped out by the left ventricle in a 1 minute period. So if more blood is being pumped out, that means more red blood cells are being pumped out. That means more oxygen can be carried. So that makes sense. If you increase cardiac output, you're going to increase oxygen flux because there's more red blood cells to carry more oxygen. And the next factor is arterial oxygen saturations. So not only is the amount of red cells important, but how saturated those red cells are with oxygen. It's like if the trucks are driving from the depot to the supermarket half full, you're only going to carry half as much stuff as if the trucks are driving from the depot to the supermarket completely full. So the greater the oxygen saturations, the greater the amount of oxygen is going to be transported to the tissues. And the third is the hemoglobin concentration. That is the amount of hemoglobin in the red cells and the total amount of hemoglobin in the blood, because it's the hemoglobin that carries the oxygen. So if the hemoglobin concentrations are high, then more oxygen will be carried. If the hemoglobin concentrations are low, then less oxygen will be carried. So in other words, if the tissues of the body become hypoxic, the body can respond by increasing cardiac output, increasing oxygen saturations, and by increasing hemoglobin concentrations. And let's think about these in turn. Let's think first of all about the cardiovascular response to hypoxia. But before we do this, we've got to go into a little anatomy and physiology. Now, underneath the aorta, there are structures called chemoreceptors immediately underneath the arch of the aorta. And these chemoreceptors detect oxygen lack in the blood in the aorta. And then you might remember that the carotid arteries, the common carotid artery, is the artery that carries blood up towards the brain. And the common carotid artery divides into the internal and the external common carotid artery. Well, just after the bifurcation of the internal and external carotid artery, on the external carotid artery, there's an artery, a small artery leaving that takes blood to a structure called the Carotid Bodies. And there's one of these on each side. So the Carotid Bodies are very small structures on either side of the neck at the bifurcation of the carotid arteries. And they receive a blood supply from the external carotid artery. And what these carotid bodies do is they are called chemoreceptors, and the aortic bodies are chemoreceptors as well. but the carotid bodies are chemoreceptors, and they detect oxygen lack. And if there's a lack of oxygen, they'll send impulses up to the brain stem to say, just a minute, there's a lack of oxygen here. So they communicate via sensory nerves up to the medulla oblongata of the brain stem. So what this means is, if the amount of oxygen in the blood drops, that's detected by the aortic bodies and the carotid bodies, and they rapidly send nerve impulses up to the brain stem to inform the brain stem of the developing hypoxemia. And then the brain stem responds to the developing hypoxemia to try and modify the components of the oxygen flux equation. And the first one is the cardiovascular response. So, the oxygen lack is detected, and what the brainstem will do, it will increase its sympathetic outflow. And if you increase the activity of the sympathetic nervous system, you're going to increase heart rate, you're going to increase stroke volume, and you're going to bring about a peripheral vasoconstriction. So when someone becomes hypoxic, there's an attempted tachycardic compensation. If the heart's beating quicker, that means more blood is going to be pumped out in a 1 minute period, and that will increase cardiac output. Because you might know that cardiac output equals heart rate multiplied by stroke volume. So if we increase heart rate and or stroke volume, that will increase cardiac output. If we increase cardiac output, we increase the number of red cells circulating around, and therefore we increase the oxygen, the amount of oxygen that's being carried around in the blood. And of course, the increased heart rate and the peripheral vasoconstriction will increase blood pressure, and again that helps to circulate the blood around more quickly. So there's the same number of red blood cells in this situation, but they're being circulated around much more quickly, which is great. It's a compensatory mechanism. Then, of course, the respiratory centre, also in the medulla oblongata of the brainstem, is stimulated. Now, the main thing that stimulates the respiratory effort is increased amounts of carbon dioxide. That stimulates it greatly, but oxygen lack will also do so. So even if the carbon dioxide levels in the blood are the same, the fact that the oxygen levels are dropping, that will independently stimulate the respiratory centre. And the respiratory centre will send nerves down the spinal cord. They'll leave via the spinal nerves to go to the intercostal muscles via the intercostal nerves. And of course the impulses will go down the phrenic nerves. The phrenic nerves, you might remember, leave the spinal cord at levels 3, 4 and 5. The rhyme is 3, 4 and 5 keep the diaphragm alive. They go down to the phrenic nerves, and that stimulates the diaphragm. Breathe faster, breathe deeper. So there's a hyperventilatory response to hypoxia, which of course makes perfect sense, because that will increase oxygen saturations. If you increase oxygen saturations, you increase oxygen delivery, because oxygen flux is determined by cardiac output multiplied by oxygen saturations multiplied by hemoglobin concentrations. Now the third part of the equation is hemoglobin concentrations. Now the cardiac output and the increased ventilatory response only take a few seconds to develop, but the increasing the amount of hemoglobin takes much longer. But what happens here is when the amount of oxygen in the blood drops, that's detected by the kidneys. Now I know it's detected by the aortic bodies and the carotid bodies, but it's also detected in the kidneys. And the kidneys respond by producing an endocrine hormone called erythropoietin. And erythropoietin circulates to the bone marrow, and it stimulates the process of erythrocytes, of erythropoiesis, which produces more erythrocytes. So erythropoietin stimulates erythropoiesis, which results in the production of more erythrocytes. And of course the erythrocytes are the red blood cells. If there's more red blood cells, there'll be more hemoglobin, and more oxygen can then be carried. But that will take time. So the body's physiological response to hypoxia can be explained in terms of the oxygen flux equation. It will increase cardiac output, it will increase oxygen saturations, and over time it will increase hemoglobin concentrations, all of which can compensate and increase the delivery of oxygen to the tissues of the body.